In this video, I'm going to discuss an application of acid-base chemistry, which is buffers. We use buffers a lot in biology to keep a solution at a specific pH, usually a pH that allows life to be maintained. And so the way a buffer works is it maintains a specific pH by doing small neutralization reactions. So if an acid is added, it will neutralize it into its conjugate base. Or if a base is added, it's neutralized to its conjugate acid. So this is going to highlight the difference here. If I have water, just pure water without a buffer system, it'll be at pH 7. And when I add an acid to it, I should see that pH drop down to something like 4. And if I added a base instead, I would see that pH increase, in this case to something like 10.5. So each few drops of acid or base will dramatically change the pH of my solution. Now, if I have a buffer solution, I'm going to have some amount of a weak acid and some amount of its conjugate base. And it's going to be a roughly 1-to-1 mixture of this acid and conjugate base, along with my water. So now, when I add some acid, it will react with the buffer's base and neutralize it. And so my pH doesn't actually change very much. It might drop a little bit, but it'll stay close to 7, right? About 6.9. Now, if instead I add a base, then it's going to react with the acid, the weak acid in my buffer system, and neutralize it. And so my pH won't change very much. It'll go up a touch maybe, but it'll stay very close to 7. And that's what a buffer does. It has a small amount of a very weak acid and in its conjugate base that'll react with acid or base as it's reacted. That's stronger than it. So again, a defining point of a buffer solution is it has an acid-base conjugate pair. So it isn't any weak acid and any base. They have to be a pair for one another. And the reason for that is as I neutralize my weak acid, it'll form more of the conjugate base already in solution. And as I neutralize with the base, it'll form more of the conjugate acid already in solution. And these will be in equilibrium with one another. And so as the concentrations shift, Le Chatelier's principle will bring this all back to equilibrium, allowing this buffer to work better than just adding any old acid-base combination. So this is a perfect example of a weak acid, weak base. So I have acetic acid. It looks like this. And acetate. So here's my acid, and its conjugate base will lose this hydrogen here. And so its conjugate base is acetate. And basically what happens is this hydrogen, if a base is introduced, bounces over here and I bounce back and forth between this acid and base. And so this hydrogen can go back and forth. And if I have acid around, it'll react with my base and it'll form more of this acetic acid. And if instead I add a base, it'll react with my acetic acid and it'll form more of my acetate base. And so that means that the primary acid-base components of my buffer system are not going to change. I am neutralizing other acids and bases into the ones I already have. These work best when they're at roughly equal concentrations. They can be a little bit off from that, and sometimes you want to do that to maintain a specific pH, but they work best when they're very close to the same concentration. So here's another way to visualize this. So I start with my acetate and my acetic acid at exactly the same concentration. And as I add acid, it's going to react with my acetate. So I see my acetate concentration go down, and my acetic acid concentration increase. If instead I added a base, it would react with my acetic acid. And I would see a decrease in that acetic acid concentration and an increase in my acetate. But my equilibrium constant would maintain a balance between these, so I would not see a very significant change in my pH. So here we're just highlighting that our acid reacts with our weak base of our of our buffer, and base reacts with the weak acid of our buffer system. So let's look at the buffer system of our blood. So our body maintains a pH between 7.35 and 7.45, and it really needs to stay within that range for our bodies to work properly. And so there's a number of mechanisms, 3 primary ones, that maintain that blood pH. And one of them is a buffer system within the blood. And that primary system is made out of carbonic acid and bicarbonate, its weak base. So here we go. So here is our carbonic acid, and here is our bicarbonate. So this is our weak acid, which is our carbonic acid, and its conjugate base, which is bicarbonate. And so within our body, there's an equilibrium between these two. If we increase the amount of acid in our blood as hydronium ion, it will react with our bicarbonate and shift this equilibrium so we produce more of our carbonic acid. So as that. And that neutralizes any addition of our acid. If instead a base was added, like hydroxide ion, then we would see it react with our carbonic acid and see a decrease there as we increase the amount of bicarbonate in our blood system. Now we have another control mechanism between this buffer system, that our carbonic acid is going to rapidly decompose into carbon dioxide. And this is an equilibrium. So if I have a lot of carbon dioxide, I can actually reform carbonic acid in the blood. And once it forms this carbonic acid, or sorry, not carbonic acid, carbon dioxide, we can exhale that. And that helps control the balance in our blood and maintain this buffer system over a long period of time. Here's some other common buffer systems you might encounter in biology. Acetic acid and acetate is commonly used. Bicarbonate and carbonate is in our bodies. Dihydrogen phosphate and hydrogen phosphate and phosphate as well. So these are all buffer systems that you might encounter in the biological sciences.